Well, it's truly a wonderful pleasure to be back here at the ICTS. I've had the tremendous pleasure of being here many times over the last 10 years, and I can't stress enough what both the revelation and an inspiration it's been to get to see a really fantastic, special, cool, fun institution spring up out of nothing into something which is this amazing place now. And so it's really one of the highlights of my at least the sociological part of my physics career, as well as the physics and all the wonderful physics interactions I've had here to see this happen. So congratulations again. So I'm going to be talking about really a circle of ideas that I've been thinking about for around almost 10 years now, and something that you've heard a lot about over the last well, many decades, but really accelerating a lot over the last 20 years, especially in the really amazing connection between theories of gravity and gauge theories in one lower dimension, theories of gravity in anti-de Sitter space and gauge theories in one lower dimension, is the idea that that space-time can't be something fundamental. It should arise from more primitive ingredients. This we've known for a long time from even more basic arguments. If you make any attempt to actually measure small distances and times, any attempt to do such a measurement puts such a huge amount of increasing amounts of energy in smaller and smaller regions of space. You eventually, inevitably, collect every such experiment ends up collapsing the region you're trying to resolve into a black hole. So we've known for a long time that the notion of space-time is approximate, but this has gotten a lot more concrete over the last 20 years. And I think sort of one slogan that people have been exploring a lot, and they continue to be exploring very actively, is the idea that space emerges more fundamentally from a quantum mechanical system. So there's an asymmetry in this picture. Quantum mechanics is king, and space emerges as the dynamics of certain kinds of interesting, strongly interacting quantum mechanical systems. That's not what I'm going to be talking about. What I'm talking about is something more speculative, more futuristic perhaps, but is something I feel is eventually inevitable. It's also something more radical, is the idea not that quantum mechanics is king and space emerges from it, but that space-time and quantum mechanics are sort of equally unfundamental, but they also emerge equally, sort of hand in hand, locked together from some more primitive building blocks. And I just want to give a few reasons why we expect something like this to be true. First of all, most of our big success in understanding the emergence of space from quantum mechanical systems begins with the sort of basic observation that when you have quantum mechanics and gravity, you can't make any precise quantum mechanical observations in the interior of some region of space. The reason is if you want to make any precise observation quantum mechanically, you have to make it with an infinitely large measuring apparatus in order for the apparatus itself not to have systematic quantum fluctuation errors associated with its finite size. And so you can't do that in a fixed size room because as you make the apparatus bigger and bigger, it gets heavier and heavier. It eventually collapses the whole room into a black hole. So you have to take these apparatuses and move them off to infinity, where they can prepare and receive the outcome of experiments. And so we have to anchor our precise quantum mechanical observables when we have gravity to the boundaries of space-time. But we have difficulties, and that works beautifully in the world which is the inside of a tin can, like in anti-de Sitter space. But it does not work for our own universe, which is accelerating. And in fact, this opens a humongous number of can of worms, not the least of which is that in an accelerating universe, we have access to a finite amount of stuff. And so we can't even make, even if we wanted to, infinitely large measuring apparatuses. So there's no well-defined notion of any kind of quantum mechanical observable that we can speak of in this kind of situation. So first of all, just experimentally, the fact that the universe is accelerating means that for a truly fundamental description, not only do we need to make sense of not just emergent space, but emergent space and time because it's cosmological, but we might even have to deal with some kind of extension of quantum mechanics to allow us to figure out how to make sense of physics in this kind of geometry. Notice that I'm not saying something stupid like quantum mechanics is modified. In any situation where quantum mechanics can give you a precise answer, I believe it will give you the answer that quantum mechanics says it should give. But these are situations involving applying quantum mechanics to the entire universe where quantum mechanics cries uncle. We don't know how to apply it, and so first of all, these are indications just from nature, from the fact that we don't live in a universe that has these nice asymptotics, that we need to do something more. Let me skip over this more theoretical motivation and move on to some more broad circumstantial clues that we should be thinking about quantum mechanics and space-time sort of more tied together. First, it's very striking whenever we teach quantum field theory in all of our courses, that quantum field theory is something that really likes to live not in Minkowski space, but in Euclidean space. That's where it's well defined. And but in Euclidean space, it's not something that's quantum mechanical. It's a statistical mechanical system, and the continuation from Euclidean to Minkowski space turns those objects into things that we interpret as amplitudes. So in other words, causality and the probabilistic quantum mechanical interpretations of things that we compute come about together. There are similar things that have been seen more recently in the context of understanding scattering amplitudes in interesting new ways, some of which we'll see later in the talk, where you actually begin with 2 dimensions of space and 2 dimensions of time. But in all the cases, the sort of 3 plus 1 is something that comes out. Or what happens as you go to 3 plus 1 is that the causal and the probabilistic pieces of the physics go together. There's other sort of broad clues lying there in the structure of the most basic observable in particle physics, which are scattering amplitudes. Now, when you imagine scattering particles at the Large Hadron Collider or anywhere else, our usual picture of it is a bunch of particles come in, they scatter, and then they go out. So there's very much a picture of a matrix, the S matrix. It takes in particles and converts them to out particles. And yet, when you compute them, the first thing you do in your graduate courses is realize that it's actually more natural to not make this distinction between who's in and who's out, treat all the momenta as being outgoing, for example. And in fact, the momenta are naturally complex. So this object with all the momenta outgoing is not interpreted as something that's an amplitude for something from going to the past to the future. Only when you go to Minkowski space and decide that some of the particles have positive energy and the others have negative energy, do you again convert these objects into something that has the interpretation of an amplitude. In other words, again, the quantum and the causal interpretation of the objects goes hand in hand. Another fact that we'll come back to is that if you want to check, someone hands you some amplitudes, you want to check whether the answer is compatible with the principles of locality, the space-time locality, and of quantum mechanical unitarity. The actual check that you have to do involves asking, for example, where the poles of some amplitude is, and that where the poles are controls locality. The fact that it factorizes on the poles into the product of lower amplitudes controls unitarity. They're intimately, totally intertwined together. So I think these are, to me, many circumstantial clues that we should think about quantum mechanics and space-time on as being more closely related to each other than we're thinking about them now. Now, in this sort of previous picture where the quantum mechanics is king and space emerges, so that picture is understood, not understood perfectly well, but it's extremely well established. There's a lot going for it. So what's new? What's fundamentally different? Well, of course, what's fundamentally different is the mystery of time. And there are many questions here, many of which go all the way back to the 1960s. A very basic one is, how is the physics of causality reflected in something like scattering amplitude? So, you're an LHC experimentalist, you wake up in the morning, you collide some protons, you go, you have your espresso, you come back, all you see is some histograms of things that came out. Well, how do you know that what happened is that first a gluon inside the proton hit another gluon, then this happened, then that happened, then the other thing hit it, and then they all came back out? That's all in your head. That's all something a theorist comes along and tells you that's what happened in order to explain the patterns that you see in the end. But there's a more invariant question. What property of these histograms, what property of the amplitudes themselves encodes causality? There's analogous questions about cosmological time evolution that I'll actually spend, if any of the students are around for the school next week, this will be a big theme of my lectures at the school, is trying to understand the answer to the question, how is cosmological time reflected in what's often pretentiously called the wave function of the universe? What I want to stress is that these are very basic questions we still don't know the answers to. We don't even know the answers to these questions in perturbation theory, when we have a perfectly well-defined quantum field theory to play with. Never mind, not perturbatively, never mind on general ground. And in fact, the inability to answer this question was the failure at the heart of the S-matrix program in the 1960s. People hoped that they had an intrinsic, they would be able to derive what the rules of causality meant from an understanding of the analyticity properties of scattering amplitudes, and they just ended up being wrong. There was no good way of sort of slavishly deriving it from the bottom up. So why are we going to do better now? There's, of course, a lot of reasons. We have a lot more data, theoretical data, experimental data, but also, I think most importantly, we have a new strategy that we're not going to slavishly derive these, what these rules are, but in fact, we're going to turn the problem on its head. We're going to try to look for some new principles, new laws, very likely involving new mathematical structures, and a different class of questions to which things like scattering amplitudes or the wave function of the universe, and hopefully even more realistic observables after that, are the answer to. And understand from these new starting points how the physics of local space-time physics and unitarity and quantum mechanics, how they emerge, and hopefully how they emerge together. All right, so let me talk about this now in the restricted context of just the question about scattering process, just to be very clear. Again, imagine my LHC experimentalist who wakes up in the morning scattering particles. They get something. The question is, what happened inside? And the theorist comes along and say, what happens inside is this mess of things happened. All these virtual particles inside, they hit each other. All this stuff went on. Things went in. Things went out. But we're looking for a different thing inside that black box, which does not involve local evolution of the particles moving in the interior of the space-time. Now, apart from these highfalutin reasons that I mentioned, why would you expect anything like this to be true? Well, one reason to expect it is some wonderful discoveries that were made by people starting around 30 years ago, that when you actually do these calculations that you need to do, and experimentalists care about in order to be able to extract physics from particle collisions at the LHC, when you actually do these calculations the way we're normally supposed to do by drawing these pictures Feynman told us how to draw, you get hundreds and hundreds of complicated pages of algebra, which after lots and lots and lots of tricks collapse sometimes to one term or three terms. Okay? So that was a clue already 30 years ago that we now know is a tip of a very big iceberg. That there is something wrong. It's not incorrect, obviously, but by making the physics of unitarity and locality manifest, as we do with Feynman's diagrams, we're hiding something else. And so that's a second indication, a more practical indication, that some different gadget in here must exist, right? There must be some other machine that produces the answers for these amplitudes, the answer to different natural questions, which is not local evolution in space-time, but is something else. All right, so what could this kind of machine look like? And here we have a very basic problem. We can get very concrete right away. So what do these amplitudes depend on? Well, there's some kinematic space of variables that they depend on. We can think of these as what labels the asymptotic particles at infinity. So this is another set of coordinates for the boundary of space-time, if you like. In this case, the boundary being Minkowski space, since we're talking about scattering in flat space. There's lots of different choices of ways of talking about this. We can use just the physical momenta of the particles. We can use twistor variables. We can label them by points that we actually see on the celestial sphere. So there's lots of choices for what this kinematic space should look like. They're all different ways, one way or another, of coordinatizing the boundary. But there's a big problem, and there's a big difference between this physics of flat space, much closer to what the real world looks like, than the world in a box that we've studied so much in anti-de Sitter space, which is that on the boundary here, we have no obvious notions of locality, no obvious notions of time. We don't know what physics, if I wanted to have a description of physics that only lived on this boundary, it can't be an obvious one. Okay? There's no notion of locality or time here, unlike the case of anti-de Sitter space, where there is. And so the theory that lives on the boundary can just be an ordinary quantum field theory. So now on this canvas, we're then led to ask the question, what kind of ideas can breed physics life into this space? I just hand you the space of physical momenta or twistors or the celestial sphere or what have you. What question do you have to ask on this space whose answer is local unitary dynamics if I'm not going to put in a Hilbert space and a space-time in the interior? All right, now that's the rough question that my friends and I have been pursuing for the past 10 years or so. And I can tell you the kinds of structures that we've run into that seem to be part of the story. Of course, there's a very, very long way to go to understand everything in real generality, but there are some things that are understood. They're not just slogans. One class of objects that's come up is an interesting set of mathematical objects that we're calling positive geometries. And the way this is linked to those questions will be, I'll explain in the context of one example in the rest of the talk, but just roughly to give you an idea of what these things are. A positive geometry is some region P in some space which have boundaries of all possible codimension. So the simplest example of something like this would be a triangle or a polygon in a plane, or simplices or polytopes in higher dimensions. Okay? Those are very simple cases because the objects are cut out by linear equations. And in fact, the example I'm going to talk to you about will fall into that simplest possible class. So we won't even have to get fancier than that, even though the first examples of these things in connection to scattering amplitudes were in slightly fancier contexts where these were more curvy surfaces. So that's why I'm saying it in some generality here. Okay, so first there's an object like this that's a closed region with boundaries of all codimension. It's a real geometry, but importantly associated with it is a certain differential form, a certain canonical form, which is unique and has a property that it has singularities, logarithmic singularities. That just means that locally the form looks like dx over x, dy over y, dz over z, and so on. In the locus of every singularity, it's just logarithmic singularities, but it has logarithmic singularities on and only on all the boundaries of all codimensions of this positive geometry. Okay, so that's what positive geometries are. And if you have a positive geometry, there's all sorts of ways of going about computing that canonical form. I'll just mention two of them. One thing you can do is you have a complicated positive geometry, but you can break it up into simpler pieces. You can quote-unquote triangulate it. Then it's a slightly non-trivial fact that if you add up the canonical forms for the pieces, they give you the canonical form for the whole thing. Okay, so if you manage to geometrically triangulate the object, then you also into simpler pieces for which you know this canonical form, then you know the form for the sum. Something else that you can do, if you have one positive geometry and you have a real diffeomorphism that maps the interior of one point by point into the interior of another, then another sort of wonderful fact is that the push forward of the canonical form from the simple geometry into the complicated one gives you the canonical form on the complicated one. And here it's very important that you sum over the preimage of all, even though every real point here just maps uniquely to a real point here and forwards and backwards, the preimage might have many complex points that you have to sum over, but so long as it's a diffeomorphism from the interior of one to the other, then the push forward of the form also gives you something. All right, so how does this positive geometry answer, or this, how does this structure go help with the question of what breathes life, physics life, into this canvas that we're talking about? Well, let's go back to this picture. We have, and we're going to see an example of this, but we're going to have a d-dimensional kinematical space, whatever it is, some capital d-dimensional kinematical space. And we're going to find that the scattering amplitude in the cosmological examples, even the the perturbative calculation of the wave function of the universe, is actually best thought of as a certain differential form, not as a function, the way we normally think about it, but naturally thought of as a differential form that lives directly on this space. Now, that differential form is completely determined by the following pieces of geometry, really ultimately combinatorics. It's really combinatorial geometry. In this kinematical space, there's going to be a big positive region. I'll explain what all these things mean, but there's some sort of space-filling positive region. On top of that, but it's space-filling, so this is capital D dimensional. This differential form is typically not a top form, so it's lower dimensional. However, there's also going to be a family of subspaces of the same dimensionality as the differential form, with the following property. A, these subspaces intersect this positive region in a positive geometry. So they're going to intersect them in something that looks like a polytope, let's say. And that's the specific example we'll see in a second. And B, the form, that's a scattering amplitude, is in fact, has a property that when pulled back to this geometry, it is the canonical form associated with that positive geometry. And that's what completely fixes the amplitude. So in this way, totally geometric, combinatorial geometric questions in this space of boundary data produce out of them physics that's local and unitary. So locality and unitarity has an ultimately combinatorial geometric origin. All right, now, there are many examples of this phenomenon by now. The first example, around 4 years ago, were called amplituhedra. And these are actually, in a sense, the best understood so far, but also the fanciest of all of them. Fanciest and also most primitive. Of course, those things usually go together. But this is associated with scattering amplitudes for maximally supersymmetric gauge theories. But just this year, we've seen 4 new appearances of these objects. There's something that whose positive geometry is actually a very old object that mathematicians have known about for back to the 1960s, known as the Associahedron. This will end up being related to scattering amplitudes for very general classes of theories of massless particles in any number of dimensions. Then there are positive geometries seen in the context of the wave function of the universe. And just in the last couple of months, analogous positive geometric structures showing up and controlling the structure of low-energy effective field theory in any consistent ultraviolet theory, and also a positive geometry that is associated with conformal field theories that seems to be related to the geometric structures that people studying the conformal bootstrap for the past 5 or 10 years have been seeing. All right, but let me, in my last few minutes, just give you a very quick flavor of what this connection with the Associahedron looks like. There's a universal feature of all scattering amplitudes, but let's stick with the simplest case of things that are just tree amplitudes. And the universal feature is, I've alluded to already, is factorization. So if you have an amplitude, it can only blow up when what you normally think of as a virtual particle becomes real. So that tells you where the poles are when the sum of the subset of momenta goes on shell. And on those poles, you have to factorize. The amplitude has to factorize into the product of 2 pieces. Okay? Now, this basic picture of factorization, of course, is something you can talk about without dressing it up with fancy things that involve momenta and helicities and all the things that we talk about when we talk about particle physics. In fact, it's a very basic combinatorial object that Jim Stashev started studying in the 1960s. And so you can ask the following question. Just imagine, let's say, here I have 4 points. This is the whole amplitude. Now I could factorize it. Imagine I'm only drawing planar graphs to the moment. So I can factorize it in one channel or another channel. And so these are the 2 ways that I can factorize it. Or I can start at 5 points, and I can factorize, have a first factorization in this way, and I can take each one of them and continue to factorize it all the way down to cubic graphs. Now, this gives you a set of objects, and you'd like to think of the ones at the bottom as vertices of something. The next one would be edges. The final one would be the interior. Okay? And the idea would be that things higher up would contain things lower down if the things lower down were contained in the were an even finer factorization of something that we had already had a partial factorization of upstairs. So we can draw all of these diagrams dually, and it's a little easier to visualize. So here we're just drawing plain polygons, and we're just triangulating them. Okay? But we can have a partial triangulation all the way down to a full triangulation. And once again, you want to think about objects with the property that the full triangulations are vertices, and all the partial triangulations are facets of various dimensionality until you get to the very top. Now, these things were studied from many, many points of view for many reasons, but this is a very basic, one very basic aspect of them. Let me just tell you a little bit more about this, and I'll tell you about the connection physics, and I'll stop. So far, I just described the object to you purely combinatorially, but quite beautifully, this network of inclusion relationships is really that of a convex polytope that lives in n-3 dimensions. That's not obvious. It didn't have to be the case, but it ends up being true. So, for example, the two examples that I talked about are shown here. The n equals 6 case is shown here again. These are all the vertices of this object, are all these triangulations, and I haven't decorated the rest of them, but it's possible to decorate everything else with partial triangulations such that everything makes sense by inclusion. All right, so there is this combinatorial object, and quite beautifully, a combinatorial object like that actually exists in that space that we're talking about, in this space of scattering kinematics. Just to give you a flavor for how this works before I tell you about that connection, let me tell you how we're supposed to think about not scattering amplitudes but differential forms. Again, if you're a particle physicist, you see these two graphs, you'd be tempted to write down 1 over s plus 1 over t. But now we're supposed to instead write down ds over s, and with a minus sign, minus dt over t. So that's the ds over s, that's relatively natural. That gives you something with logarithmic singularities, d log s. The minus sign is there in order to actually ensure this form is well defined on the projective space of s and t. In other words, it's only a function of the ratios of s and t, as we see in this case. It's just d log of s over t. And this kind of picture extends to summing over all the graphs. But if we now go back to the space of just the kinematical variables, then first of all, I'm going to have a positive region where all the poles, which I associate with the sum of all the ordered momenta, here represented by xij, all the ordered momentum from I to j squared, they're all positive. And this particular dot product of any two non-adjacent momenta, I and j, are to be set to a negative constant. Okay? So that now gives you a shape. And the intersection of this set of hyperplanes with this positive space is actually the Associahedron. The very simplest case is at 4 points where the positive region would just be s and t positive, and here we're instructed to set s plus t to a positive constant. And so the intersection of these two things is just that line interval. Okay, so literally what it looks like in some examples. But now there's a unique form on this big space that pulls back to a canonical form of the Associahedron on the subspaces and gives the amplitude. This projective invariance that I told you about is actually a hidden symmetry of something as dumb as the phi cube theory. This cubic theory, which I certainly never thought had any interesting structure in it, actually has a small hidden symmetry which is associated with this projective invariance. And Feynman diagrams are actually one particular triangulation of the Associahedron. And they're a triangulation that actually involves introducing an artificial plane at infinity. And by doing that, they actually break the projective invariance term by term. It's only a feature of the sum. So just so you see that it's not just pushing around pictures, here is the explicit expression that you would get at 5 points, let's say, if you sum Feynman diagrams. But each one of these turns out to have some spurious poles at infinity. But there are other expressions that you get by triangulating the Associahedra in these two cases. Quite amusingly, there's an expression that's even shorter than Feynman diagrams. I didn't think that was possible to get smaller than Feynman diagrams in something as dumb as this phi cube theory, but it's even possible to do it here. And there are more complicated looking expressions as well, but they all have a purpose in life. This expression, term by term, makes this projective invariance manifest. And this expression is even better. Term by term, it makes the projective invariance manifest, as well as the surprising vanishing of the amplitudes in a particular particular limit that I don't have time to discuss. Okay, so there is a geometry that controls the amplitude. Different triangulations of it make different features manifest. One of which is Feynman diagrams, but there are many others which are not. All right, so that's an example of this general structure. Again, there was this positive region where all those poles were positive. There was this subspace that I defined. The intersection of these two is literally a geometric shape. And there's a differential form that pulled back to the subspace is the canonical form associated with the Associahedron. So in this sense, very, very concretely, the Associahedron can be thought of as the analog of what we were before calling the amplituhedron for maximally supersymmetric theories for this cubic scalar theory. All right, I think that's all I will have time for. There's analogous stories for the physics of gluons. There's a very interesting way in which this geometry allows you to replace the Lie algebra group theory factors that we normally talk about with scattering amplitudes with these differential forms instead. So there's really a geometrization of color. And there's also an Associahedron that's famous to string theorists that have known about for a long time. In fact, if you think about the open string worldsheet, the boundary structure of the open string worldsheet at tree level is that of an Associahedron. And you can wonder, given that we have these two Associahedra in town, whether there's any relationship between them. And there is. They are one is mapped into the other by some equations that David Gross and Mende introduced back in the late 1980s, but which have been studied again very intensively from different points of view over the past few years. And this diffeomorphism between this worldsheet Associahedron and this space-time Associahedron gives an interesting derivation of some fascinating equations for scattering amplitudes that people have been playing with over the past. So let me end just by going back to this picture. So what breathes physics life into this space? In all the examples that we've seen so far, there's something fundamentally combinatorial underneath it. It's more abstract and more primitive in the case of the amplituhedron even than what we've seen for the Associahedron. They're clearly related to each other, though, for reasons I don't have time to explain. There's something fundamentally combinatorial associated with that of the positive geometry. And finally, the connection to physics comes from this canonical form. But what I want to stress, in every one of these examples, we've seen this phenomenon of locality and unitarity being locked together, that you cannot separate them. They're sort of one object and one set of questions, and they always give you things that are local and unitary at the same time. So I have no idea how general this is, but it's no longer being seen in just one or two isolated examples. We're seeing it. We're seeing it in a number of places, and I'm interested to see where it goes in the next number of years. Thanks a lot.
We are running very much behind time, so I will restrict this to just one or two maximum.
Mine is actually two questions, Nima. One about...
I'll answer them quickly.
Right. One about the future and one about the past, because those are the two parts I understood. This is the future thing. How does this relate to your colleague, Niti Seiberg's big scheme, the new quantum field theory foundation, where he's also interested in emergence of space-time automation, and he also wants to solve the hierarchy problem as a side effect. Is this related to that or completely unrelated?
Well, I mean, to the extent that there's clearly a lot more to quantum field theory that meets the eye. So at that level, everything is everything's here. I mean, here there's a difference. There's a difference in that all the questions here are all ones which are not Euclidean. They're questions where time matters a lot. Okay, so now quantum field theory has all kinds of observables, beginning with Euclidean correlation functions or partition functions on complicated manifolds or whatever, right? Mm-hmm. Presumably there's some gigantic animal that will help us understand all those things in a new way, because there's magic, ancient magic and more modern magic in those places too. What I find interesting is that when you ask not fancy questions about partition functions on complicated manifolds or Euclidean questions, you ask questions that experimentalists care about every day of their lives. Those questions also involve rather alien objects, sort of interesting structures that we're not normally used to running into in physics. I think this is important. Nature, nature has time. Nature looks pretty close to Minkowski space in some approximation. Closer, it is cosmological. So I think the real step, the biggest magic, if any of this is on the right track, the biggest magic should be seen in cosmology and not in scattering amplitudes.
So the quick second question is about the past. I liked your analysis of S-matrix theory kind of failed. I always thought S-matrix theory failed because everybody left it after Tufts' work when people realized quantum field theory really works, right? I mean, and
I'm giving a physics, not a sociological answer to the question. I mean, I'm saying that if you read any of the books with the title "The Analytic S-Matrix,"
right,
you'll see what the problem is with this program, because they, at the heart is we will determine the S-matrix by the consistency conditions of analyticity. What are those conditions? Damned if they know. So they cheat by staring at Feynman diagrams. Okay.